That's okay. Yeah, I think you probably forgot the time, but that's okay. Yeah, can you join now? Okay, please. Yeah, I will transfer to you. I start the first couple of slides, so don't worry about that. Yeah. Okay, thank you. And okay, so let's resume from here. So you see the first page is about what's a graph theory. Let's start with the vertex and the edge, and we talk a little bit about that here. And then the second one is different type of the edge. So that means you have the direct connection or undirected connection. One is with the direction, another one is only the association that have no direction. Okay, and then we are talking about what's really the graph theory. And of course, we already know what's a graph. Graph means you have the connection of the vertex. Vertex means each point, and you have edge. So here is each line is called edge. And so in between of this, we call the connection, right? You draw a graph, something like this, they do not always have to have connection. That's perfectly fine. Okay, so when you see this, we will have some sort of the representation. That's really what we really need to pay attention to, because most likely you are not really
oh yeah, I can.
You are not really draw the graph on the paper. Instead, you can convert as some kind of context. So this is really the context you can convert to. You have a whole set of vertices, and you have the edge between this vertices. So for example, you have A, B, C, D, E, F, and then you have the connection, say A, B, A connect to B, and you have AD, A connect to D, and you have BD, B connect to D, CF, C connect to F, and then FG, same thing, F connect to G, GH, G connect to H, and GE, G connect to E, and HE, H connect to E. So all of this are really say you have the vertex. So that's each point. And then you have the edge. So you will really understand this edge is called the undirected edge because they have no direction, right? Okay, so that's pretty much about the first couple of slides talking about graph theory. That's very, very basic one. And now I will ask Yan to present the rest of the first topic, the graph theory. Yan, are you ready?
Yeah, I should be.
Okay, do you want to share your screen, or you can ask me to flip the page? So that's perfect fine.
You're just gonna have to hold on one sec while I get this stuff.
Okay, sure.
Just one moment.
Okay, how about I finish this page so you are prepared to start from the next one. So don't worry. Yeah, we can really work out together. So the edge of the above graph here and here, they are different, right? So you can see. Oh, actually they're the same. I'm sorry, they are not different. It just looks different, but they're the same. So you are really know that they have no direction. So that means you have the connection from the A to B. It's the same as B to A. So they have no direction. And also you have a path from the vertex X to Y. It's really, you should build that as a whole list. So that means you have two lists. One list is vertex, another list is the edge.
Yeah, I should be good now.
That's how you represent the whole graph. So you have the list of the vertex and another list of the edge. And yeah, Yuan, let me know if you are ready. So
I'm ready.
Okay, so you want me to stop sharing? You can start sharing that?
Yeah.
Okay.
Let's see here. Is this working?
Yeah, I can see it.
Cool. So I think this is the slide that you left off on.
Yeah.
So yeah, so this slide talks about terminology, and then So let's see here. So if you go back to this graph, yeah, so it's talking about this graph right here. So if we see, if I'm circling two of these two are called connected components. So these are called connected components. So that's right. Let's highlight that for you. Those are connected components, those are called. So if you can see, we have A, B, D, and C, E, F, G, H. So those are the two connected components. If we go back here, we can see we have A, B, D, and then C, F, H, G, E. So those are connected components. And then a cycle is just a set of vertices that loop around. So if you can see, it gives us H, E, G, H as an example. If we go back here, we can see we have H to E to G to H, and then that just gets back to where we're going from. So that's considered a cycle. And then, so there's multiple ways to identify a cycle. We have right here, HEGH and EHGE all refer to the same cycle, but we've just rearranged it. So another piece of terminology we have is that it's here is what's known as a tree. So you can see right here, up here, the definition is that there's only one path between any two nodes on a tree. So say if we look at this node and this node, the only way for us to get from this node to that node is through here and through there. We can't get there any other way. So then it also says another fact about trees is that a tree with n vertices contains exactly n minus one edge. So if we take a look at that, here we've said that this is a tree. So if we look at this, we have 1, 2, 3, 4 edges, 1, 2, 3. 4 vertices and 3 edges. We look at this similar tree over here. We can label that 6, 7, and then you can see we come out to a count of 8 vertices and then 7 edges. If we have several disconnected trees, like shown on this right picture right here, then we have what's known as a forest. So these are all independent trees. Whoops. So we have 1, 2, 3, 4. A weighted graph, as it says down here, is a graph that has a weight or a cost. It says, so we can say we would be able to illustrate this if we can get a new page here. Say we have one node here, one node there, one node there. We could say this has a cost, so like 100. Maybe this has a cost, maybe 20, and it's not necessarily dollars, but it could be any number really. So that's a weighted tree. And on this weighted tree, say the $100 could represent like flight prices. So say the flight to this city to that city is $100. That would be a weighted graph. We could have another one, say 30, and it can all have all the features of a graph. Like we can have loops here. We can have basically everything that a graph has, except it just has numbers associated with every edge. That's really all that's different. And a spanning tree, if down here, is a subgraph that contains all of the vertices and forms a tree. So let's see what's best to illustrate this. We can go back here. Let's take a look at this graph here independently, this connected component, and say we can take a subset of these nodes, say just G, F, and C. This would be a spanning tree because it's a subset of the nodes, and it's also a tree. It doesn't have any loops. If you want to go to C to G to C, we have to go through G, F, and C. So that's what a spanning tree is. So a graph, so here's what adjacency matrices are. So to represent these graphs, these are in picture forms, but we also need to kind of have like an actual way to represent these as data. And adjacency matrix is one way to represent this data. So how we have an example adjacency matrix down here. So what this is saying basically is that if you can see, we have letters, nodes at the top and at the side. So if we have here, if we look at A and B, that if there's a 1 there, that means that the A and the B is connected. We can see up here, A and B is indeed connected. Look at B and C. It also has a 1, so B and C are connected, and that is true. We can also take a look at, say, what if a 0? So C and A is a 0. If you can see C and A, they are not connected. So that's what an adjacency matrix is. So there's also a different way to see the adjacency matrix. You can see here we have m squared, but it's not really m squared. It just means that the default adjacency matrix with nothing in it just means how can you, if you can get from A to B with just one move. In this case, we can go to A to B with just one edge. So the m squared represents here is it asks, can we get from A to C with 2 moves? And if we look at the graph up here, we can get from A to C with 2 moves. It's from A to D to C. All right. Yeah, so we got that. And right, the 2 also means here there's 2 ways that we can get from A to C. So we can also get from A to B to C. So that's what the m squared means here. And if we have a B to B, it means there's only one way that we can take 2 moves to get from B to B. And in that case, it's just going to be going around. All right. So here's a problem we have, and it asks us to find a number of different cycles contained in the directed graph with vertices A, B, C, D, E. It is that. So, well, the solution's already on the slide, if we can look at it. A, B, A, B, C, B, D, and C, D, C. So those are the only cycles that we have. 1, 2, 3. That's the 3 cycles that we have. I mean, the solutions are on the slides. So in the following directed graph, find the total number of different paths from vertex A to vertex C of length 2 or 4. Well, let's try to do this without looking at the solution. So let's see here. So we want to get from vertex A to vertex C, and we can either do it in 2 or 4 moves. Well, so one way we can do it is we can see here that A has a loop around here. So then technically we can just say that we can go, that means we can say that we can go from A to A. So that means, say if we go from A to A to C, that would be a length of 2. And that would count as a valid solution. That's this one down here, A to C. I mean, it's that one. I don't know why that solution is incomplete. So, oh, that's in the length of 4. Never mind. Well, let's see where it is. A to C. That's this. And then, so those are the only ways we can use 2. If we look at 4, we can just expand upon this A to A thing. Just say A to A to A to A to C. That's 1, 2, 3, 4. Yeah. So that's down here. There's a different way. You can say we can go from A to C to A to C. It's basically going to be going from A to C, back, then going back, then going back, and moving. So just moving back and forth. And that's another length of 4. So you can see that's how these problems work. So here we have a directed graph. So you can see these have arrows in them. So that's how you know they're directed. So it asks us to, given the adjacency matrix, draw the directed graph. And it's already drawn for us here. We can do it ourselves. So we have A, B, C, D, if we label this down here. We get the nodes A, B, C, D. So A to A has no connections. A to B has 1 connection, so we draw an arrow going from A to B. A to C and A to D. A to D has 1 connection, so we draw another line here. B to A has a connection, draw a line. Then B to D has a connection, so draw another line there. C to A has also 1 connection, so we draw a line. And that's, the rest is none. D to B has 1 connection, so D to B. Then D to C also has 1 connection, so like that. The resulting diagram looks a bit complicated because we haven't arranged our nodes properly, unlike the diagram down here. That's just a clearer version of what I just drew. But that's the way you do a directed graph. And I think those are the end of the slides.
Okay, great. Thank you. I will start share my screen and we continue for the second topic and third topic. Okay.
Excuse me, I have a question.
Go ahead.
So can I annotate?
Yeah.
Okay, I don't have permission to annotate right now.
If possible, would you please just
Okay,
post
so
in the chat if that works for you? Oh, that's too challenge.
no, could I? So if I had like, can I just ask it like right now? Yeah.
Sure.
Yeah. So if I have like a figure 8 pattern sort of, and I go like I circle it around it, and like the thing in the middle of the figure 8, that vertex gets repeated once. Is that technically a cycle because it's even though it's repeated, is it a cycle, or is it not supposed to have repeated vertices except for the first and last one?
Yeah, without draw a graph, probably it's a little bit hard to
I think maybe I can share my screen and see if you can draw on that. So
yeah.
Can you like stop sharing for a second? Oh. Yeah.
How about that?
Can you take a look? Can you annotate on my screen?
Oh, yeah, I can do it now. Okay.
Yeah. So can we get a blank page? Just draw on that.
Okay, let's say I have and I go from here to here to here to here, here, here. Is that a cycle? Because you're repeating this point once.
So we have multiple cycles here actually. So let me just draw one for you. So here we have one of these cycles. And then over here, we should have another one of these cycles. So that's, I think, how this cycles work.
Okay, so it can't have like a repeated thing in the middle, right?
Well, I
mhm.
think there's might actually be 3 cycles because like there's the big one,
Yeah,
right?
the
It goes in figure 8, and then there's
outside
the
one.
2 triangles.
We can take a look at the definition of a cycle again. If I go back.
So if it's
Well,
like
a cycle is basically when it starts and ends at the same point. So yeah, the big
Yeah.
one is a big one because like well it starts and ends at pretty much you could just choose a point and then go around. But then the smaller ones, yeah.
it's like the
Yeah, so here's the definition we have again, which is simple except that the first and last vertices are the same.
okay, so basically you can repeat points in the middle, right?
Yeah.
Then if I had something like I saw this on the homework basically. So if I had a cycle here, and there's another thing here, wouldn't I technically have infinite cycles if I can repeat, because I could just go like one cycle and then go to this point and then 2 cycles and then go to that point and 3 cycles and then go to that point and so on? I don't know,
What do you
like,
mean by going to this point?
so
Like,
you're going
which point are you starting on?
around. So we're starting here and we're
Yeah.
going around this triangle like multiple times and
Mhm.
then looping to and finally going to this point.
Well, I don't think that would be a cycle because we're like starting and ending on different vertices, right?
Oh yeah, I forgot about that.
So it would be a cycle, but we could say have a cycle. Well,
But-
let me get a new page here.
Oh wait, would that be a path then?
Yeah, it would be a path. So if we have, that's not what I want. If we say have A, B, and then another thing C here, we have arrows like that, then technically you could say that A, B, C, A is a cycle. And you could also say that A, B, C, A, B, C, A is another cycle. Then you can just keep adding like vertices onto this. So yeah, you could say that there are infinite cycles in this.
It's infinite? Okay. Really? All right.
So yeah.
Because in the previous problem, I remember like there was a question, so can you like go to the question slide? Like there was the one with the
Let's
question.
see. Which one was it? Let's see.
No, I think he's talking about the homework assignment. How about that? Since we have limited time here and we have to cover more topic, if you have question, would you please post on the Google Classroom so we can discuss over there. So not really hold the meeting for too long, because I know today is really Monday and a lot of students have to finish some homework. So we cannot really host a meeting for more than 1.5 hours. That's probably a little bit too long. Yeah. Okay. So yeah, let's stop here and I will pick up the another 2 topic. If you have any question, Jason, you're definitely welcome to post on the Google Classroom, discuss with your peer, and also Yang and I will try to answer your question. How about that?
Okay, sure.
Yeah, I will also post the answer of the homework, so don't worry about that. The whole reason I don't repost the answer of the homework is because I do not really want to post that so you lost the motivation to finish the homework. But we only have about 10 days to prepare for the contest, so I will post the answer, so don't worry too much about that part. Okay, so the first topic we already finished. It's about graph theory. And after that, yeah, any student from the elementary group, you can drop, since that's the only topic we cover for the contest. But for the junior group, please stay over here. we will talk another 2 different topic. The second topic is called the digital electronics. The name's a little bit confused, so don't get confused by the name, but most likely you probably see that if you are learning, I don't know how many of you are really in high school, but if you in high school, you learn something like the logic gate, you probably already know that what a digit circle is. So the digit circle really it's a name we referred here. And we use the logic gate to perform some function, what we call the Boolean logic based on the input. So for example, and or X or something like that. So I will try to be a little bit fast since we are running behind the schedule. Okay, so the first 2 of the gate, what we are talking about is really, the first one is something called buffer, but actually you can think it's really like the variable assignment. So that means A, get out of this buffer or get out of this gate, it's just the same. So that means A is 0, it's still keep as 0. A is 1, keep as 1. Or you can see if they have a dot here. So that's really something what we call not. Not means just reverse. So if A is 0, it will become 1 as the output. If A is 1, it will become 0. And then the next 2 is very, very important, but also I try to make sure you understand that as a fundamental theory. One is called AND. I'm sorry, not these 2, but combined with this. Okay, the AND means A and B. So if you learned the Boolean table, Boolean algorithm before, you know what AND means, right? AND means it only true if both are true. So that's really represent here. A and B means A is false, B is false, it becomes false. A and B, if one of them are false, it's also false. A and B both true, the output X will be true. So that's AND. So if you write this down, AND, you can use the dot to represent here. So that's really the dot here. Oh, you don't really use dot. That's perfect fine, but most likely I suggest you to put the dot here. So you remember that's AND. Also, they have the not AND. What that really means? It's really as simple as you have the output from here and then you reverse. So you can see you have the AND is false. So the not AND become true. So do here. AND is false and then not AND is true. But if AND is true, not AND becomes false. And just remember, they have the dash on top of the A and B. So that's how you write it down. So when you try to simplify that, you have the dash on top of that. And then we were going to this logic gate, what we call the OR gate. Just remember, the AND gate, you see the tail here is straight, right? They have no curve. And the OR gate here have the curve. The rest of that looks, this is more smooth, and this is really the edge. But just remember, if you don't really very sure, you just see how the tail looks like. If the tail looks like a moon, right? or like a curve, that's OR. OR means A or B. As long as one of the A or B is true, it becomes true. So that means only false when both of them are false. If one of them are true, it becomes true. So that's OR, right? You already learned the Boolean algorithm, so you should know that. And here is not OR. It's really like the not AND. So that means they have a dot here, then it's just reverse of the output from the OR. So if OR is 0 or false, it becomes true. if or is true, it becomes false. So that's really how it works. And you should pay attention to how it was right. So it's really right like this, A plus, so that's or. And if you have the not or, that means A plus, and you have the dash on top of that. So just remember how they are right. And you use a dot, or you use plus, okay. And then here is a little bit tricky. If you see the logic gate like this, you know this is really something like you have the curve. So this is or, right? So without, if you remove this second curve, so that's really the or. But if you add the second curve here, that's really called the XOR. XOR means you get the X and Y. If they are different, that becomes true. If they are the same, that becomes false. So that's really how logic there works. Logically, A and B, if they are the same false, they become false. If they are same true, they become false. But if they are different, one is true, another one is false, they become true. So that's really XOR. And then here is even a little bit more confused, but don't worry too much about that. This is pretty much just like XOR, but with the reverse. So that's not XOR, right? So we also call it exclude OR. So this is really reverse of this. So you see here they have the false, true, true, false. Here become true, false, false, true. And what's really the logic understanding you can think is that if both are the same, so if both are false, they become true. If both are true, they become true. But if both of them are different, they become false. So it's a little bit hard to understand at the very first try, but please try to practice a little bit more. You will get used to it, and you can see how to represent that. Of course, this one is a little bit challenge when you try to type in or write as a homework. Okay. And then we'll move here as a practice. So this electronics, the whole series is trying to solve the logic gate problem. Some of this major, like the EE electric engineer, they have to study that. But as general, the computer science also need to understand what's that. So let's try to break this down and see how we can really work out on that. So I don't really know how to make the annotation. Let me try see if I can bring up the tool. Oh, okay, annotate here. I'm sorry. Yeah, here. Okay, so this is A, right? And this is B, and this is C. And the first, what's the logic gate of the first? So we break down. So what's the first logic gate? So if you go back to here, you probably see that the first is not, right? Okay, great. So the first is not. Yeah, I tried to ask you guys to give me the input so we can work together. So out of the first, we get what? We get A, not.
A, not.
So not A. So we have not A here, and then from B, go over to here. What's this? This is not curve. I'm sorry. They are not
and.
Okay, so that's and, right? So we know this is and. So that's really what we know from here. I'm sorry, from here. That's and, right? So we know this is and sorry.
I think it's or since.
Okay, so this is and. Oh, gee. Sorry, I'm not very good on that. So you can see this and why I cannot use it? annotation draw. Okay, draw here. Okay, so this is A, not A and B, right? Curve. Okay, and B. Okay, so out of here, that's what we get, right? Okay, not A and B. So let's move down to here. What's this? So we know B is input, C is input, and this also is AND. But after AND, they have a NOT, right? So let's step by step. So we have the B and C, right? I'm sorry, this is not very clear, but you can see the dot here. And then after that, they have NOT, right? So this how we represent here. So we, oh, I'm sorry, I got AND. Is this something we reversed? I think this is something
Yeah, like I said, I think it was or, not and.
Yeah, I think this is or. Yeah, this is not. Yeah, this drawing is not very good. I'm sorry. Yeah, this is or. Yeah, that's my bad. This is or. So do here. This is or. Yeah, this drawing is not very good. So looks like and, but okay, but actually it's or. So you have this top one like this, not A or B, and this is B or C, not B or C. Okay, so you put all this together. This is AND, right? So this is AND. AND means you have a dot in between. So at both sides, you have A, not A, or B. And this part is B or C. Okay, so this is how this comes from. So when you try to make the representation, you try to break down step by step. So don't rush, it will be there. So after that, we will really use something what we learned before. Very, very important one part is from here. So this will be converted as not B and not C. Okay, so this will be converted like this. That's very important. So if you are not purely understand that, try to use logic gate to make the conversion. So this will be converted to this. Okay, so that's why you see the second part becomes this. So this is second part, right? So this go over here. Okay, and now we can use multiplication. That's very simple, straightforward. So you can see this not A, right? Not A will times or say or not B, not C. So that's all, right? So this is this part. So this part is really this times over here. So apply over to the not A. So do the second part. The second part is really this apply over to the B. So the B or not B or not C. Then we comes with something very, very important. I like to emphasize this because this will make your solution much faster. Whenever we see the digit in electronics, something like this, you have two of the OR, but both of them are reversed. So that means you have A or not A. You have B or not B. This becomes what? This becomes 0. So whenever you see this, this becomes 0. Of course, 0 times 0 or another one is still 0, right? So you get from here the still get 0. So that's why the second part, this part, it's really 0. And you only have the first part. That's why the answer is this. Okay. So there are 2 keys. The first key is this one, how to convert from the AND to OR. And the second part is that when you see the have A or not A, B or not B, something like this, you know they will get 0. As long as they become 0, 0 or another different condition, still 0. So that's why you get rid of this one. Okay, so that's, I know it's a little bit tricky when you work out the solution at the first try, but try to be a little bit more, pay a little bit more attention to the details. I'm sorry for this drawing is not very good, but actually this first part is all okay. So yeah, when you try to solve the problem, try to step by step break it down, and there are a couple of very important steps, and after that you will get used to it. Okay, and then this one clear or join. Okay, so this is another practice. So for this practice, of course we have all of this logic gate, right? So we will have the A here, A, B, C, and very simple, straightforward here. It's not A, right? So we already know that this is not A. And then from here is A. This is OR, right? A or what? A or B, right? So this get out of here is what? It's really say A. I'm sorry, this is a little bit small, but A or B. Okay, and then you get A or B, and this is AND. And not A, so you get from here that's A and not A and A or B. I'm sorry, that's my bad. I'm not really good at that. Okay, so this is really this part. So this is really, this part has been built up, right? So you can see this part has been built up. And then we go to the down side of this part. What this really means. So the input is B, input is C, and we have the OR here, and then we have a NOT. So that's not OR, right? So let's build the OR first, and then is this the OR? I think that's OR. Yeah, the graph sometimes not really very clear. Okay, so this is OR, yes, that's OR. So OR B or C, and then you have not B or C. Okay, so that's become not B or C. And of course, this is really the curve, it must be. Okay, so then you have this part and this part. The condition is AND. So that's how they are joined together. So this first part is this top part. The second part is this part. So to here. Okay, so now we already write down, we know this first is good. So how we can break it down and make it simplify? Then we can just do it step by step. The first part first. So we do this like not A or A, and not A, sorry, or B, right? Okay, so this is really how they are moved to the next step. And if you still remember what we learned from the previous one, this becomes what? Think about that. What this becomes to? not A or A, where it becomes
0.
zero, right? So this will becomes 0. So we only have not A or B. So that's how this end by not A or B. Okay, so you see this part, it's really how it was left over. Of course, it's this part. And then we're taking care of the second part. The second part is the same thing. If you remember what we learned last in the last example, this second part is really can be converted as B, sorry, or not B or not C. So if you have the end here with a not, you can convert as this. Okay, so that's very important. So this is really go to the second part here. That's how you get everything here. Now you have the not A or B or not B or not C. And then it becomes a little bit tricky because you have the B or not B. This part alone will make it becomes what? Just like this, not A or A will becomes 0. B or not B will becomes what? Do I get lost the connection or you are just thinking about that? This will become the same, like what's the result from here is it's a 0, right? So if you have the not A or 0 or not C, in the end, it becomes another 0. So that's why the answer is 0. Okay, so I know 2 examples is really not to give you too much help, but we don't really have too much time. So that's why we only give you this kind of sample, but you will need to practice a little bit more to really purely understand of that. Okay, so let me clean up that. And let's go to the third topic. The third topic is really repeat many times, and it's really how the program doing. That's something I really like, but on the other hand, a lot of times you probably feel a little bit struggle. And I give you a quick suggestion. If you really have time for the 5-question section, you create a small program to solve that problem, because you can use the table to solve that. So that means you have the ABCD and you write on the output for each step by step. I prefer to use the programming to solve that, just because that makes it much more visualized. Okay, so I skipped the first couple of slides because we really come over that many times, and then we go to the topics. And the topics, the sample here is really like this. So you have a string like bananas or any other string. So this string can be changed. And then we have a program, something like this is what we call the pseudocode. So we know we would like to reverse and come from the last character, reverse back, and then create another list. So this list will be like pretty much like reverse this string. And then in the next loop, we will try to count if at any same position or same index, they have the same character. If they are the same character, we just add 1 for the number. So we are really
okay. I have a question.
Go ahead.
Can I annotate?
Sure, go ahead.
I can't annotate.
Oh, you cannot?
Yeah.
Yeah, because the setting, the security setting. So you probably can put in the chat.
Okay, yeah. So it's fine. So line 3, it says for j equals length a -1 to
Mhm.
0, step -1. How would you like model that in Python? Because
That's a great
because
question.
usually when I'm doing these questions, I usually like to model it in Python because this is pseudocode. So
Yeah, that's right.
if it's like for length a-1, that's an integer, but how would you like, I know there's a way to do it, but like I don't know how. So for like an integer 2, 0, so you're going backwards because it's at step -1. Can
Yes.
you explain how to do that?
Yes, that's a great question. I will illustrate that part. So this is really, oh, sorry, why it didn't move. Okay, so this is really the code. And let me try to bring up and running that in with the online IDE. So it's just a simple one, so I can use this. Okay. Okay, I have a simple code here. It's pretty much the same. Okay, so you can see, I try to compare to here, so you don't get confused. Okay, so you can see A is bananas, and then you have number is 0, and you have T is an empty string, and then that's answer your question. You do not have to put that inside the loop. Of course, I use the while loop. You can use other loop, it's okay. And I can create a variable which, as you have the assigned the length of the a -1. Do you understand why they use the length of the a -1? Do you understand what's the reason for that? Why they don't just use length of a? Instead, they use length of a -1. If you don't know, don't worry. I just raise this as a question. And
so yeah, it's because oh well, could you could do it like in there right now, like hold on, let me type in the chat. Could you do well,
okay, so let's run this.
oh, could you like do that as well, like I type in the chat?
Okay, so if you do that, how can you keep change the j? That's a problem, right?
Okay, so use because you need to change j, so you just said
Oh yeah,
before.
that's right. Yeah, the whole point we break that down to j -1 every time is because when you use a loop, you are really use the loop to keep track of the a at the index of j, right? So this is very important part. Even there are pseudocode like this, they don't show you what exactly you're supposed to do, but actually you're supposed to have the step -1. So that means you need to have the j -1, so it will be from the backward count. Let me try to demonstrate that. So you.
I see. So in Python, you just have to like put that like inside the loop. So like you're iterating through, and then j equals j plus or -1. But in C, it's more similar to the pseudocode.
Yes, that's right.
So in C, it's like if start, stop, and then the step. And so it's like 1 plus plus or -1.
You're right. Okay, so let me break down step by step. So this is really next statement. So you can see the first is really assignment. So the A is bananas and number is 0. And then T is empty. So let me run. So the T is empty string, right? And then you can see what's a J. J is really 6. Why the J is 6? It's because the length of this is what? It's really 7, right? B 1, 2, 3, 4, 5, 6, 7. So length is 7. The whole point why they use the length of a -1 is because what's the index for the last character? So if you want to write the like the AJ, what's the last one? What's the last index supposed to be? Is that 7?
S.
So what's the index for this one? I'm sorry.
That's 6. Yeah, that's 6.
Yes, that's 6. It's because it's based on 0. So the first one is 0, right? 0, 1, 2, 3, 4, 5, 6. that's why you use length of A minus 1, because that's how you get the last in the last character, right? So, okay. So now you get the J is 6, is larger than 0, large or equal to 0. And then you got T is plus AJ. So what's the AJ now? AJ is really ace, right? So the T is empty. T plus ace is ace. So now you get it. Then the J becomes 5. Then you go say, oh, J is larger than 0. And then the AJ is this one, is A, right? Because the 5 is A. So you plus that, append that to the end of the T, becomes ace A. So do here. So I just quickly go over. So ace A, N A, N A, B. Okay, so that's really, the T now is really the reverse of the A. So if you're thinking about that, right? So you see the A is bananas, but T is ace A, N A, of course, the meaningless, but it's really the reverse of bananas. Okay, so now your end. And you can see when it's end, the J becomes -1, because the last time the minus one more time from 0. 0 minus 1 is -1, but we cannot really use that. So we have to reset the J as 0. Then we can use J again. Of course, you can use any other number. I want to stick with J just because this is pseudocode, so that makes a little bit more sense, right? So now you have the J is 0, and then J is smaller than length A minus 1. So length A minus 1 is still what? What's the number of this? Length A minus 1.
6.
That's 6, yes. So now J is 0, 0 smaller than 6. That's perfect. So we will compare AJ to TJ. So AJ and TJ, what's the AJ? What's the TJ? When the J is 0. Thinking about that. Okay, so actually we can print this AJ, and we can print TJ. But before I really print that as next run, you can make the guess. So J is 0, AJ is what? A at 0 is B, right? And TJ, what's TJ? T is ace A, N A, N A, B. So the T at 0 position is ace. So the ace and B is not equal, right? So you are not really add on top of, you are not really increase the number. So you just move on. Now you can print out that. Of course, this is not displayed here just because this is a new code add-on. But the second one is what? Now the J is 1. So the AJ is what? J is 1, AJ becomes A, right? So that's character A. And TJ is what? T is here. TJ, T at 1 is also A. So now A is A. So because this is A, this is also A. What they will do? They will add.
Also,
I add the code here, so it becomes meaningless. But you can see the number add 1 becomes 1, right? So okay.
Oh wait, so
that's really
wait,
how
so
the calculate.
the while J less than length A minus 1. So that's it. So it's while J is less than 6, and then
Yes.
J is increasing.
That's right.
From 0 to, and then if
this condition,
if the two characters if they match, then you add 1.
That's right. So they are really use this to calculate how many of this reverse string and the original string at the same position, they use the same character. Okay.
So
for
if you're
example,
going
don't-
backwards, then it's j equals j minus 1, but then going forwards, it's you add 1.
That's right. Okay. So actually we can even make a little bit tricky, just say, oh, I am who I am. Okay, so if we're running something like this, so what's the number you think there will be? Of course, it's a little bit tricky, but actually, if you are really know how this program works, you can write on the paper and you can get the answer, right? So I am who I am. Okay. So make the guess. Yeah, we play this as a game. So we play it together. What's the number will be? So this is really how much of this character when they are reversed, it's still the same.
I think 5.
You think 5? Let's run.
Oh, wait, for the different one. Oh,
Yeah. Yeah, for
oh,
this
not 5.
So now it's 3. Yeah, actually it's 3. But actually, yeah, this is very interesting. So it's really something about how to do a quick programming. When you are really find something here, you don't really just directly use whatever they suggest, because they suggest here step -1. You have to convert that. So do here. You have to convert that as the original start variable. So you have to give them a assign. I'm sorry. As a length -1. Okay, so that's really how our third topic, what we are talking about. You are really supposed to understand how the program works. You can either draw on the paper or you can write a small program if you have time. So either way can solve the problem. Yeah, I think that's pretty much covered today's topic. I know we are running a little bit late, but hopefully you get my point. And to wrap up, for junior group, you have 3 topics. The very first one is the graph theory. And of course, if you go to check your homework, you probably know how they are really ask you to solve the problem. And then the second part is about the digital electronics. And most questions is something like this, how to simplify it and get the answer. And the third part is, of course, the programming. So you understand how to write a program, or they don't really ask you to use Java or Python, as long as you can understand the logic. But I would strongly suggest you to can solve the problem in both approach. So that help you to both solve the problem purely on the paper or solve the problem with the coding. So either way, I don't really know which one works better, but I would suggest you to train your mind to think like a computer. Okay, that's probably not the right term, but anyway, your logic mind is supposed to able to convert this pseudocode into a piece of code like the computer code. That's what I mean. Okay, so that's pretty much covered all of this topic. And I know we have probably 7 days to 10 days. We can prepare for the next and final contest. I hope all of you have a great evening. And if you have any question, please post on the Google Classroom. And yeah, we will try to work hard and finish the last contest. No matter what kind of output you get, don't be frustrated if you are not as good as what you think. But you already, believe me, you already much better than most of your peer. So that means most of the friend, if they never learned that before, they never practiced this kind of theory before, they don't even know what's a graph theory. They don't really know what's a digital electronics. They don't really know how to solve the problem like this. So yeah, to be just proud of yourself. You are really one of a kind. So yeah, I believe you guys. It's really big, excellent job. Thank you so much. And special appreciate to Yang. Thank you, Yang. Okay, and yeah, you have a great night and see you guys later. Bye.
Thank you. Bye.
Thank you.
Thank you.
Bye.
Bye.
Bye. Thank you.
Thank you.
Bye.
Bye.
Goodbye.